Hey guys, this is Mr. Barthold, and this video is to go over Faraday's law and Lenz's law in more detail, go over some practice problems that we haven't quite had time to get to in class, and then also to discuss a further extension of Faraday's law for a special situation of a moving conductor. And that's section 21-3 in your book. In each of these, remember we've talked about magnetic flux in class, right, where the flux is defined as the magnetic field multiplied by the cross-sectional area. And again, you're looking for the component that is, this angle represents, how much of the field is actually crossing through this cross-sectional area due to any angle that may be between the surface and the field. So, we're gonna be using that. So Faraday's law is basically that the change in magnetic flux generates an EMF. And remember, an EMF is just, this is just a voltage, right? A battery has an EMF, 9 volts would be the EMF for a 9 volt battery. And so anytime that you are changing the magnetic flux through a surface, you are going to generate a voltage or an EMF across that surface. And so there's two ways to do this. First off, we can change the magnetic field, right? If flux is, well, first off, let's so remember Faraday's law. Let's switch to blue here. I like blue better. Faraday's law is that the EMF induced is the change in flux over a certain amount of time. Right, so if you're going to change this flux, right? Remember, flux is a magnetic field times area. So there's two ways to do it. You can change the magnetic field, or you can change the area, right? The cross-sectional area. So we are looking at the first case we're looking at is changing the magnetic field. So this is going to be the change in the magnetic field times the area over the change in time, right? So the magnetic field can change over time. We're going to look at an example very quickly, and that will generate a potential difference or an EMF across across a conductor of some sort. The first that we are going to look at is this patient, and so imagine you have a patient taking an MRI scan, which is a magnetic resonance imaging. So there is obviously a magnetic field involved, and the bracelet specifications, it has a certain amount of electrical resistance. It's made out of copper, 0.01 ohms, and a certain size, diameter 6 centimeters. We're going to assume that this is a circular bracelet. So kind of imagine that you're lying inside of an MRI machine, or you've seen pictures, and the magnetic field will run along the axis of your body. And so if your arms are by your side, then it will be, you're kind of imagine yourself lying down, and the magnetic field is running along your body, and your arms are along your side with the bracelet on there. So the magnetic field will actually be going perpendicularly through the bracelet surface, which is important, of course, to signify that the flux will be at its maximum, that there's no angle between them. So during the scan, the magnetic field changes. And let's say it reduces from 1 Tesla to 0.4 Teslas in about a second. Then what would be the effect of the current? What direction and what strength will the current be through the bracelet? So let's draw a quick little picture depicting the bracelet. So this is a circular bracelet, as we are going to say. And imagine that, so the field is running from head to toe, right? So the field will be, this is the bracelet, and you're looking down towards the feet. It's kind of, imagine here, the field is going to be directed into the page here. All right, so imagine you're lying down, and so the field is directed into the page. All right, so the first question we can ask is what, so this field is reducing in strength, so it is decreasing. So this is a changing magnetic field. So the first question is, what direction will the current flow? So this is using Lenz's law. We practice this in class. You should pause the video here and use your right-hand rules and try to determine which way the current will flow. And hopefully you determined that it will flow clockwise. All right. So why is it flowing clockwise? I'll try to explain this as, it's a fairly complicated law. Not complicated, just a little confusing. So Lenz's law. And so if the field is decreasing into the page, then it's basically the same as the field as if it were increasing out of the page, right? So the field is getting larger, so I'm going to increasing out of the page. So that means that the loop is going to act in a way to resist that. Remember, so the loop itself will generate a field. The current induced will be such that it will increase into the page. So the current flux will increase into the page. And in order for that to happen, your right-hand rule will tell you that it is a clockwise current there. All right. So next we're going to determine the strength of this field, and we will do this using Faraday's law. So Faraday's law, that the EMF is the change in the flux over the change in time, and in this case we're looking at the change in the magnetic field. All right, so the form that we're looking at is the change of the magnetic field over time times the area. This is the change in flux over time, and so it's pretty clear to see that the area, well, it is a circle, right? So pi r squared. So pi times the radius squared. The radius is 0.03 meters. And we're going to square that. So that is the cross-sectional area of this bracelet. The change in fields is what final mass? So we're going from 0.4 teslas, and we began at 1 Tesla. So subtraction there. And then the time which this occurred was 1.2 seconds. All right, so we've changed the field by that much over that amount of time, and that field is going through that cross-sectional area. And so this EMF comes out to be about 1.4 millivolts, or 0.0014 volts. So that is the induced EMF. I believe the problem was asking for the current. And so now that we know the current, obviously the other part of the other specification of the bracelet was its resistance of 0.01 ohms. So current is voltage divided by resistance, or the EMF over the resistance. And so dividing that by 0.01 ohms will give you 0.14 amps. So 140 milliamps will be flowing through this bracelet in the clockwise direction as a result of the changing magnetic field and the changing flux through that bracelet. All right. So the other way to change the flux is to change the area, right? So we've already looked at an example where you change the magnetic fields, and so if flux is B times A, and we're looking at the change, then we can look at the change in the flux, which in this case we'll look at the change in the magnetic field times the change in the area over the change in time. So yeah, and that's just the other side of the coin. You can change either one, and so we'll look at example 1 of your homework problems. We'll go over that one right now. It's number 2 in your book, and we'll go over that. So you have a 16 centimeter diameter loop, and this wire is in a magnetic field of strength 1.1 teslas, and you remove it from this field over a certain amount of time. So again, we are inducing an EMF. We are changing the field through the loop by removing it from the field. Right, it is decreasing the strength of the field through the area. So what is the EMF? We will use Faraday's law. So change in flux over the change in time. And again, we're looking at, in this case, the change in the area over the change in time. So this is actually a very simple problem. The magnetic field is 1.1 teslas. And the area change, if we were removing it completely from the field, right, it is a zero, technically it's the final area is zero, right? So the change is just the entire area itself. So this is going to be another circle, so pi times the radius squared of 0.08 meters squared, divided by the time in which we are doing it. And so, what does this come out to? So let's see, we got pi times 0.08 squared times 1.1 divided by 0.15, and that comes out to 0.147 volts. So a pretty simple problem there. Just looking at the area change. Obviously, if we pulled half of the wire out, then we would have reduced the area would have changed by half that much, and it'd be half the voltage, and etc. So there's a specific type of problem that can arise out of this, and these problems have kind of sprung about on the AP test over the years. This is in section 21-3 of your book, and so you have these, I guess this called rail of wire here, and then you have this gray bar with a certain amount of resistance that is moving along this rail in some way. And so the questions of how much current and in which direction will they flow. The direction should be pretty easy. Maybe pause it to determine what it is. All right, the direction of the current should be counterclockwise. Right, it is, if we are making if the block here is moving to the right, then it is increasing the area. So the flux, which is the field, is pointing into the page, right? So the flux is increasing into the page, and so the current would have to increase out of the page to counteract that. And your right-hand rule says that will flow in this direction, right here. And so how much current flows? So there's kind of an interesting little trick that you can do using using Faraday's law. If it's the change, obviously we're not changing the field, so we're going to be changing the area. So it's going to be the field times the change in area over time. And so let's say that this block moves, and there's this picture is on page 627 in your book, or a picture similar to this. Let's say the block moves, to this location right here. I'm going to kind of color this in. So here's the block right here. We have changed the area over a certain amount of time. What is the area that we are changing? Well, we have, I guess, this length times its width, right? This is a little rectangle. This is the width, this is the length. So length times width. So that would be the change in area that we've just increased this this flux through. And so what do we actually have? If we can actually simplify this a little bit to be times, the length has not changed, right? The length of this bar has not changed. What has actually changed is the width of this area, right? So the vertical height does not change, but the width does change. So really, this is like delta W is what's actually changing, divided by delta T. And so what is this right here? This is actually a representation of velocity, right? We are changing a distance in a certain amount of time. This is a velocity. And so you can actually get another expression of Faraday's law for a moving conductor, and that is that of the magnetic field multiplied by the length of whatever is of the conductor that is moving, and then times the velocity in which it is moving. And all of these are actually vector quantities. And so yeah, this is an interesting. Remember, this is an interesting, almost special case kind of problem that can arise. And I mean, in problems of this sort, I think there's an interesting one that you should read. It's on the page 628 in your book about the airplane, and the fact that an airplane is a conductor made out of metal. It is moving through Earth's magnetic field, and so the motion of that actually will generate a potential difference across the wings. It's an interesting application that even I wasn't really aware about until reading that. So problems of this type aren't incredibly difficult, but it is an important concept to understand. Another thing to kind of understand is that inside of this bar you have an electric field that's generated. I'm going to go to the next page here. And so I'm just going to redraw this very quickly. So here's this rails, and then here's this bar, right? So if we have induced an EMF, and we said that EMF was counterclockwise, right? So the current is going to be flowing, or we said that the current is flowing counterclockwise. Then in this gray bar, we have actually induced an electric field, right? This would be like the positive terminal of a battery. This would be like the negative terminal, so that the conventional current flows from the positive and into the negative. And so we actually have an electric field that points like that inside of this conductor. And so you can have, for instance, an equilibrium, or the electric field will be generated such that it is in equilibrium, because there's not going to be a net vertical force, for instance, on this bar. And so we can actually set up, knowing that the electric field is the force over the charge, right? Now we have all of the, these charges inside of this conductor. Maybe the little electrons inside the conductor, they are moving inside of this electric field. So we have a moving charge in an electric field, or the force of which is given by Q times V times B. And so the electric field strength that is actually generated inside of this bar is, once we cancel out the charge, how fast it's moving times the field that it is moving in. So that's another little application, and we'll discuss that a little bit more detail in class. So hopefully this video kind of cleared up a few things or helps you along with your homework. And Faraday's law is relatively straightforward, but has very important applications, especially with motors and like that airplane thing, just small little medical applications. So it's pretty far-reaching. Lenz's law is a little tricky at first, but I think once you kind of practice it, makes a little bit of sense. So I will see y'all guys in class. Goodbye.